Hello and welcome. In this video tutorial, we're going to be looking at the notes for AP Physics 2 Nuclear Physics. Please remember to pause or rewind the video as necessary. Let us begin. In order to take a look at some of the nuclear concepts, we need to take a look at certain aspects of Einstein's theory of special relativity, as many of these concepts relate to Einstein's ideas in energy, nuclear ideas in energy. So there's a connection we have to establish. Section 25.2, postulates of special relativity. Consider the following situation that involves three cars traveling with the speed shown. Consider the following situation that two cars and a photon travel with the speed as shown. Okay, so let's talk about the situation on the left first. So we have car A, B, and C. First question, in whose reference frame is this picture drawn? Well, any of these three cars could be traveling at a constant speed. So this is one of Einstein's postulates of special relativity, is that all inertial reference frames are valid, which basically means inertial reference frame is any reference frame in which an object is traveling at a constant speed. And when you're at rest, you're traveling at constant speed, and A and B could very well be at a constant speed as well. So all of those reference frames are valid. Now, is it easiest to make the reference frame with respect to car C because it's at rest? Sure, probably. But the reference frame involving A and B are equally as valid. To car B, what is the motion of car C? Well, car C appears to be moving behind car B, specifically 10 meters per second backwards, because car C is at rest and car B is moving forward. So from the perspective of somebody in car B, car C looks like it's going backwards at 10 meters per second. To car B, what is the motion of car A? Well, car A is moving 20 meters per second faster than car B. Therefore, car B would specifically be viewed as moving 20 meters per second forward or in front of car B. In the picture on the right, we've got a photon traveling at c, the speed of light, a car traveling at 0.8 c, which means 80% of the speed of light, and then we have a car at rest. So in whose reference frame is this picture drawn? Same concept. All three reference frames are valid because all could be traveling at a constant speed. Car B, well, to car B, the motion of car C would specifically look or appear like you're moving at 80% of the speed of light backwards. Okay, car C would be. And then to car B, the photon would be looking like it's moving 20% of the speed of light, or 0.2 c, forward or in front of the car B. What are the two postulates of special relativity? Well, the postulate basically is, it's not necessarily a hypothesis, but it's kind of a grand untested idea. Think of it that way. But it's not necessarily a prediction as a hypothesis would be. It's simply a statement, a grand statement that has not really fully been tested. Well, Einstein's postulates of special relativity, number one, the laws of physics are all the same in all inertial reference frames, which kind of goes to what we were saying earlier. The speed of light, all reference frames are valid. Okay, all inertial reference frames are valid. Number two, the speed of light in a vacuum is measured to be the same in all inertial reference frames. The speed of light in a vacuum is measured by observers in different inertial reference frames is the same regardless of the relative motion of those observers. Section 25.4, time dilation. Section 25.5, length contraction. In order to get into certain elements of nuclear physics, meaning mass energy equivalence, we need to have a fair understanding of what relativistic energy and what relativistic mass are all about. And so a short discussion in the concept of special relativity and introducing time dilation and length contraction as the obvious starting points. And then we can get into relativistic mass, relativistic momentum, relativistic energy, all of which will show themselves somewhere along the line in terms of the nuclear reactions that are involved. So let's begin by taking a look at this short video.
Supported by Prudential. Let's say you're waiting for a friend of yours to arrive on a train. And I should point out, it's very much a hypothetical train. For one thing, it's moving towards you in a vacuum. And somehow it can travel at half the speed of light. But your friend, Bob, is on this amazing hypothetical train. Oh, and the front of the train has a headlight. From Bob's perspective, standing on the train, the light from the headlight is moving away from him at the speed of light. So the train is moving at half the speed of light, but at the same time it's shooting out light from the headlight that's moving at the speed of light. You'd think that from your perspective on the platform, it would look like the light coming from the headlight was moving at 1.5 times the speed of light, because it would have its own speed plus the speed of the train. But that's not true, because light always has to move at the same speed through a vacuum from any perspective. So from your point of view on the platform, that light wouldn't look like it's going faster than the speed of light. It would just look like it's moving at exactly the speed of light. As counterintuitive and strange as that sounds, special relativity explains why. The theory of special relativity was proposed by Albert Einstein in 1905. It explains the behavior of things that move very, very fast, as in a significant fraction of the speed of light, where regular Newtonian physics doesn't always apply. It's called special relativity because it only applies to specific situations where the different frames of reference aren't accelerating. They're called inertial reference frames. In our train example, the two reference frames are the perspective of someone standing on the train and someone standing on the platform. Neither reference frame is accelerating, so they're inertial, and so special relativity applies. Now, special relativity is built around two main assumptions or postulates. The first says that the laws of physics are all the same in all inertial reference frames. It doesn't matter whether you're on the train or on the platform, the same equations will apply. This has to be true because there's no real way to distinguish between reference frames. For all Bob knows, from his perspective on the train as it passes the platform, he's sitting perfectly still. While the platform zooms past him, or the platform could be staying put while he moves past it. The first postulate tells us it doesn't matter. The physics will play out in the same way no matter what. The second postulate says that the speed of light in a vacuum is the same for all observers, about 300 million meters per second, always, whether or not the light source is moving. Physicists have tested this fact with lots of experiments. It's definitely true all the time. So even if light is coming from a train that's moving at half the speed of light, the light itself is still moving at about 300 million meters per second. And this is where things start to get weird. You already know that speed multiplied by time equals distance, but special relativity tells us that when it comes to light, speed is always constant, which would mean that the other two variables would have to change, time and distance. And they do. When time changes, that's called time dilation, and when distance changes, that's called length contraction. Time dilation occurs when another reference frame is moving relative to you. So time in that reference frame slows down relative to the time you measure. You can see why if we go back to Bob's train. Say Bob stands on the side of his train car that's closer to the platform, and he's facing a mirror on the opposite side of the car, 5 meters away. He shines a flashlight towards this mirror, which reflects the light right back towards him. From Bob's point of view on the train, the situation's very simple. The light traveled straight to the mirror and back, a distance of 10 meters at the speed of light. Sure, looking through the window, you saw the light travel to the mirror and back, but meanwhile the train was still moving. While the light traveled towards the mirror moves sideways relative to your spot on the platform. And while the light traveled back toward Bob moved even further sideways. The result is that you saw the light travel diagonally, as though its path formed two sides of a triangle. From your point of view, the light traveled a greater distance than it did from Bob's point of view. But special relativity tells us that the light's speed was exactly c, even though it traveled a greater distance. And if the light traveled a greater distance at the same speed, then it must have been traveling for longer. You and Bob are both timing the exact same series of events, but you're measuring a longer time than Bob is. So from your perspective on the platform, time has slowed down for Bob. That's time dilation. If you measure the distance the light was travelling from your perspective on the platform, you'd calculate that time slowed down for Bob by a factor of 1 divided by the square root of 1 minus the train's velocity squared divided by the speed of light squared. We'll call this factor gamma, and it applies to any situation where another inertial reference frame is moving relative to yours. Time in that moving reference frame will seem to equal time in your reference frame multiplied by gamma. Gamma always has to be greater than 1 because the velocity of the moving reference frame always has to be less than c, the speed of light. So time is slower in that moving reference frame. Because time can pass differently for people depending on their frame of reference, there's also no universal concept of simultaneity. In other words, something that seems simultaneous to you might not be simultaneous to Bob. Say you see a flash of lightning at each end of Bob's train at the exact same time he passes you on the platform. I mean, we're already talking about a train going half the speed of light, so let's say it gets struck by lightning too. For some reason. You see both flashes at the same time and they're both the same distance from you, travelling at the same speed. So you can conclude that lightning struck both ends of his train at the same time. But from Bob's perspective on the train, that's not what happened. Because while the light is travelling from each end of the train to his eyes, he's moving. At the moment that you see both flashes, Bob has already moved past you, so he's seen the flash from the front of the train, but only that one. Then he sees the flash from the lightning that struck the back of the train. Light always moves at the speed of light, no matter what the reference frame is. That's the rule. So to Bob, lightning must have struck the front of the train before it struck the back of the train, even though they seem simultaneous to you. Does your brain hurt yet? As if time slowing down wasn't weird enough, there's also length contraction. Length contraction means that if something is moving relative to you, its length in the direction that it's moving will seem shorter than it would if it wasn't moving. So you might have measured the train to be 100 meters long before it left the station. If Bob measures the train from where he's standing, it would be 100 meters long. But from your perspective on the platform as it moves past you, the train will be shorter. Let's say you want to measure the train as it moves past the spot where you're standing on the platform. The train is moving at half the speed of light. That's set. From Bob's perspective, it takes 666 nanoseconds for the train to pass you. Velocity multiplied by time equals distance, so Bob calculates that the train must be 100 meters long. Now you try taking the same measurement. The problem is we already know that time moves faster for you than for Bob. While 666 nanoseconds pass for Bob, only 577 nanoseconds pass for you. And if the train takes 577 nanoseconds to pass you while it's moving at half the speed of light, it must be 86.6 meters long. In general, when something's moving past you, its length in the direction of its motion will be equal to the length you'd measure if it was standing still divided by gamma. Length contraction happens for objects moving at regular speeds too, but it's so tiny that there's no way you'd ever notice it. If the train was moving at 150 kilometers per hour, it would contract by less than a picometer. That's 100th of the length of a hydrogen atom. Since length contraction isn't something we see in everyday life, it isn't part of our intuitive sense of physics. So special relativity tells us that because light always travels at the same speed, time dilates and length contracts to compensate. Space and time, they're directly connected to each other. That's what people mean when they talk about four-dimensional space-time. If you're describing something physically, it's not enough to just talk about its position in three-dimensional space. You also need to take time into account. A lot of this might seem counterintuitive, but that's because we're used to seeing the world at much, much slower speeds than light. All of which is to say that when you start to analyze things that are moving fast, the universe becomes a very strange place. Today we learned about special relativity. We went over its two postulates and their consequences: time dilation, a lack of universal simultaneity, and length contraction. We also
So we saw in our video that time dilation refers to essentially a clock moving slower. Again, this is relative to a particular observer. So one thing we saw in the video is that we have a certain value called gamma. Okay, and gamma is 1 over the square root of 1 minus b squared over c squared, where c represents the speed of light. Okay, and so for a time dilation concept, the delta t relative to an observer moving at the speed of light is equal to gamma times delta t for an observer who's considered at rest. And so if we just kind of do a quick little example here, you can see. So as an example, let's say we have an object moving at 0.8 c times the speed of light. Okay, and what I would do is I would figure out what v squared is, because I have to plug that in here. So v squared would be 0.64 c squared when I square both 0.8 and c squared, I get 0.64 c squared. And figuring out gamma, I would have 1 minus 0.64 c squared over c squared. You can see c squared is going to cancel. And 0.64, if I take 1 minus 0.64, I get 0.36. Okay, and if I take the square root of 0.36, I get 0.6. So far, gamma is essentially 1 over 0.6, which is essentially 1.67. And so if we looked at the time, let's say the time relative to an observer, at rest is, let's say 1 year. That means for an observer traveling at 80% the speed of light, or 0.8 c, it would be gamma times this 1 year, or 1.67 times 1, or 1 2/3 of a year. In other words, time is going to appear longer to a person who is moving near the speed of light. Okay, now length contraction, as measured relative to another observer moving near the speed of light, the length of the object will appear to be shorter. Okay, now for this one, the length, right, would be the proper length. The proper length L naught is the length as measured by an observer at rest, divided by gamma. So if I use the same gamma with something approaching the speed of light at, let's say, 80% of the speed of light, we already know that gamma was 1.67. And so let's say you had a 100-meter long object divided by 1.67, right? That object would appear only 60 meters long. Okay, so for instance, to give you a good example of this, if you were, let's say you were in a spaceship traveling the speed of light and you passed by the Earth would not look like a round ball. It would look like a very super skinny oval, like a cat's eye almost, very, very super skinny. All right, so on the grid below, draw a spaceship at rest, draw the same spaceship moving near the speed of light. So let me see here. Okay, let's go ahead and draw the spaceship as, let me see, I'll draw the spaceship like this. We'll have the end of the spaceship right here, 2 units long. The tail part of it will be 2 units long. We'll make the body of it 2 units long, and we'll make the nose of it also 2 units long. So I'm making the spaceship symmetrical, but I'm making it purposefully 2 units, 2 units, 2 units. Okay, and so if you're traveling at 0.75 times, or if you're traveling near the speed of light, however that fast that is, then the length of this thing gets shortened down significantly to something that looks like this. Right, and you can see how the spaceship looks short and squat. So as we mentioned in the video, or as was mentioned in the video, if you had that hypothetical train moving at 0.5 the speed of light, so the train was moving at half the speed of light, and it had headlights that were shining in front of it at the speed of light, you might say to yourself, well, I mean, logically speaking, we should just add them together, and a person standing, perfectly still on a platform as this hypothetical train passes by would see something moving at 1.5 times the speed of light. With that, of course, that is not true. So what we're going to explore right now are what are called velocity transformations. Section 25.6, velocity transformations. So we see that we have, suppose car B has a launcher that can launch a ball at 0.75 c. That means 0.75 times the speed of light. Now suppose car B is moving at 0.75 c and launches the ball. What do we know for sure about how fast the ball is going relative to car C's reference frame? Well, in a normal Newtonian reference frame, that means slower speeds. You would simply add the speeds together, but we can't do that in this case because 0.75 plus c, nothing's going to go 1.75 c. Nothing goes faster than the speed of light. We know for sure that car C's reference frame in business is that it will be moving faster than 0.7 c, but it's going to be going less than the speed of light because nothing can travel faster than the speed of light. So we actually can quantify this too. U represents the speed relative to one observer. That's equal to V, the speed relative to both observers, plus U prime, the speed relative to the other observer, over 1 plus U prime times V over C squared, where this is going to be 0.75 C, and this is going to be C. So if we kind of plug into this, we get, now you'll notice that at really small speeds, at very slow speeds, what ends up happening is this number becomes closer and closer to zero. Because at very slow speeds, you have a very small numerator over the speed of light squared, so that whole thing goes to 0 plus 1, which basically means all of this pretty much goes to 1, and you can see you're just adding the speeds, right? Just adding the speeds. If we had a car moving forward at a speed of 10 meters per second and it launches a ball with the ball launches with a speed of 5 meters per second, right? The velocity, the relative velocity addition would be 15 meters per second because those are very low speeds, right? Not only relative to each other, but well, yeah, the V, the speeds relative to each other are really, really super small, which makes this whole thing pretty much go to 0. But when we're talking relativistic speeds, meaning approaching the speed of light, they're much, much faster. So let's go ahead and compute this example. So we're going to go essentially add these together, and we have 1.75 c over 1 plus, and then we have c times 0.75 c over c squared. We get 1.75 c over, okay, now on the bottom, we get 1 plus 0.75 c squared over c squared. You can see that cancels. And look what we end up with. 1.75 c over 1.75 c squared. Actually, the c squareds cancel over 1.75. Which basically means, right, we're the light that's traveling from this car, right, the light, that the ball that's traveling at that speed, right, it's going to go at the speed of light. It can't go any faster than the speed of light. That's simply how fast it's going to go. What does this mean about the speed of light? The speed of light, this was the second postulate, the second idea, assumption, and that's the speed of light has to be the same in all inertial reference frames. Section 25.8, relativistic energy. Now we can start to put it into play in terms of how this will work with regards to mass energy equivalence and the relativistic connection there. explain the equation E equals mc squared. Well, E equals mc squared is referred to as the energy mass equivalence. Now, when it's written like this, then it's E naught equals m naught c squared, because this is called the rest energy, meaning it's the energy that you have essentially mass that is converted into energy. But it's rest mass, meaning a mass that, as would suggest, that's at rest. Now, as an object approaches the speed of light, then what we have is we have energy, relativistic energy, would be equal to gamma times E naught, or the rest energy over the square root of 1 minus v squared over c squared. So you'll see how this kind of works, or how we can use it. What happens to an object's mass as it approaches the speed of light? Well, okay, same idea. Mass, relativistic mass. So mass, as an object approaches the speed of light, the mass becomes relativistic mass, not Newtonian mass. Newtonian mass is, slow speeds or no speed, right? Relativistic mass is approaching the speed of light speeds. And same idea. Relativistic mass is gamma times the rest mass, or the rest mass over the square root of 1 minus v squared over c squared. Okay. In other words, when an object approaches the speed of light, the kinetic energy approaches infinity. Therefore, the relativist expression for kinetic energy explains why no object can move faster than the speed of light in a vacuum. The work that needs to be done to accelerate this is infinite. The rest mass of an object is the inertial mass the object has when it is at rest. So let's explore these connections and figure out what the graphs need to look like for the following ideas. For this particular example, we have a spaceship of mass m naught and length L naught travels to the right through space with speed v. There is a clock on the ship that ticks every t naught seconds in its own reference frame. To an external observer, the ship has mass m, length L, and a clock ticks every t seconds. To an external observer, the ship has kinetic energy K and momentum P. Draw graphs representing each of these quantities of the ship's speed. So what we can do with this one is we can actually sketch this out based upon what each relationship looks like. Okay, so if we're talking about mass versus V, and we look at the equation for it for relativistic mass, it's m naught over 1 minus v squared over c squared. And what is this equation really telling you? That once you approach a certain value, okay, which that certain value would be c, okay, I want you to think about this. As v approaches c, then v squared approaches c squared, right? And c squared over c squared is 1, and 1 minus 1 is 0, right? So in other words, when we take this and we divide it by essentially a 0 denominator, then we get an infinite mass. So as the object approaches the speed of light, right, the denominator gets closer and closer to 0, which basically means the mass becomes infinitely large. And we can represent that the following way. We start with m naught right here, and literally at about 0.30, 0.40, somewhere around here, it's going to transition from rest mass, because we're only at about 30% the speed of light. That's not too fast. And as soon as we get around 50%, right, it starts to rise, and then 80%, it starts to rise, and then it's infinite mass, right, as it approaches C. Time dilation is really pretty much the same thing. Okay, as time goes on, right, we're going to start with our proper time of T naught, but then as we get closer and closer to the speed of light, the time extends infinitely long, right? And as we approach the speed of light, as V approaches C, think about that. This becomes C squared. This becomes 1. 1 minus 1 is 0. And as V becomes C, delta T approaches infinity, becomes, and that's true for a lot of these situations. As V approaches C, right, mass is infinitely large. It's going to be the same thing with kinetic energy. Relativistic kinetic energy. Okay, but now keep in mind, you're starting with 0 energy, not starting at any value. So we're starting down here, and it's approaching an infinitely large kinetic energy. Same thing with momentum. Now with momentum, it's a little bit different. Okay, so relativistic momentum, we have mv, right? But on the bottom, you've got the gamma factor of 1 minus v squared over c squared, and as v approaches c, momentum, right, becomes infinite. But at small speeds going up to about maybe half speed of light, you're going to get fairly linear momentum, meaning it's going to be starting at 0, fairly linear, and then it's going to start to really take off at that point. But for the first section over here, it's gonna climb rather slowly. The opposite of all of this, of course, would be length contraction, because all of these other values are increasing infinitely, but that's not true with length. See, length is dividing by the gamma factor, not multiplying by it. So this would be L naught times 1 minus v squared over c squared. So as v approaches the speed of light, that means what? This whole thing goes to 0, which means length goes to 0. So if we start off with L naught right here, as we approach the speed of light, it's going to drop off that way towards 0. Section 25.9, Doppler effect for electromagnetic waves. Suppose an astronomer looked at two galaxies. One appears more red than the other galaxy should appear, and the other appears more blue than the other galaxy should appear. What does this mean? A galaxy that would appear more red would appear to be moving away. Okay, why is that? Because red has a higher wavelength, which means a lower frequency. Okay, and when we learned about Doppler effect, we know that when an object that's making a noise, when a sound, right, is moving away from an observer, the pitch of the sound, the frequency, appears lower than it normally is, right, which would correspond to a higher wavelength. This is because the waves are perceived as having a higher frequency and a lower wavelength, right, would appear reddish in color. The opposite is true for a galaxy that appears more blue, right? So a bluish galaxy would be appearing to be moving toward an observer. Section 28.2, a new particle and a new nuclear model. Okay, so now we get into the nuclear physics. We have to get into essentially the nuclear components and how we essentially how those nuclear components interact with other nuclear components. So we have to start off with the basics, okay? Nuclear components, what makes up the nucleus. So let's start off with this. What is an atomic number? What is atomic mass or mass number? Atomic number represents the total number of protons in the nucleus. The mass number represents the total number of nucleons. That would be protons plus neutrons. Okay, so again, what is a nucleon? Nucleon is the total number of protons and neutrons. There we go. Okay, for example, two examples of nucleons would be an alpha particle. An alpha particle is a helium nucleus that consists of 2 protons and 2 neutrons. That gives you a mass number of 4. But it has 2 protons, so the atomic number would be 2. So how you write this, if you have element X, okay, and A and Z, this is the mass number, this is the atomic number. Okay, another example would be a uranium nucleus that consists of 92 protons and 146 neutrons. So we put 92 here, uranium has a symbol U. We put 92 protons, the atomic number is 92 down there. And if we add those protons and neutrons together, you get 238, which goes for the mass number up above. What is an atomic mass unit? State its conversion to kilograms. Well, one atomic mass unit, which is labeled U, 1U, is equal to 1/12 of the mass of a carbon atom with 6 protons and 6 neutrons in the nucleus, including the 6 electrons in the atom. And so in terms of kilograms, one atomic mass unit, 1U, is equal to 1.660539 times 10 to the negative 27 kilograms. Section 28.3, nuclear force and binding energy. Explain the nuclear force. Well, some attractive force must balance the electrical repulsion between protons. See, in the nucleus, all we have are protons and neutrons, and protons being positively charged want to repel each other. So there's got to be some force that's resisting this electrostatic repulsion. This force would be the nuclear force, okay? And this has to be an attractive force that's not only attracting protons together, but neutrons, which essentially have no charge. So we call this attractive force that's countering the repulsion a nuclear force. What is binding energy? Explain this term using nuclear potential energy. Well, the magnitude of the energy must be added to ionize the atom is known as the binding energy of the hydrogen atom. The nuclear potential energy plus the electrical potential energy is going to be positive since protons repel each other, plus the kinetic energy of the protons and neutrons must be negative. The binding energy of the nucleus is the energy that must be added to the nucleus to separate those components. What is mass defect? Well, the symbol we're going to use for mass defect is a delta M. And basically what it is, mass defect is the difference in mass between what makes up the atoms what makes up the difference between the constituents of the atoms as hydrogen atoms and neutrons and the mass of the atom itself. Okay, and you see the mass defect show up in nuclear reactions as what's referred to as the mass energy equivalence. Okay, you'll see that play out shortly. Section 28.4, nuclear reactions. How do we represent a nucleus that takes part in nuclear reaction? Well, show the nucleus representation for carbon-14, whose element symbol is C, has 6 protons and 8 neutrons. Well, the symbol we use for that, for any element is just a generic X, and we use the actual symbol, that represents the element. A represents the mass number, and Z represents the atomic number. Okay, and so for a carbon atom, you use the symbol C, right? But it has 6 protons, so we put the atomic number 6 down here, and 6 plus 8 would be a mass number of 14. We put that number up there. What two conservation laws must be obeyed during all nuclear reactions? Well, the two conservation laws that must be obeyed during all nuclear reactions are conservation of charge. That would be for the atomic number because protons are charged particles. And conservation of mass. Why? Because this is the mass number. Okay, so conservation of mass is telling you the mass stays balanced in a nuclear reaction. Conservation of charge is telling you the number of protons stay balanced in a nuclear reaction. The following are fundamental particles that take place in nuclear reaction. Label their atomic number and atomic mass. Draw a picture. Okay, so the proton, right, has a symbol P, and essentially it is a hydrogen nucleus, okay, and it's referred to also as protium. And the symbol for that is going to be the hydrogen atom, or the hydrogen symbol H. And since it only has one proton, put an atomic number of 1, and it has no neutrons, so 1 plus 0 would be a mass number of 1. Okay, now that would be essentially a proton. Okay, now you could, although we refer to it using if the proton itself doesn't include any neutron, then that's the symbol just has a mass number of 1. The antiproton, anytime we're dealing with antiparticles, it's the same mass but opposite charge. So for this one, the symbol is going to be P, and I guess we could use a symbol P for a proton too, but I tend to like to use a hydrogen atom for that because that's what a proton really is. It's just a hydrogen nucleus. And so for an antiproton, we're just going to use P. It's going to have a mass of 1, but it's going to have a charge of -1, opposite the charge here. Okay, an electron. Now, an electron, we're going to use the symbol E, just like you see here. It has no essential relative mass whatsoever. In fact, think of it this way. An electron is so tiny. The actual mass of an electron is roughly about 9.11 times 10 to the -31 kilograms. That is so much smaller than the mass of protons and neutrons that you could kind of make an analogy as follows. If you were to stand on a bathroom scale and weigh yourself, right, record your weight, and then somebody comes and puts a feather in your hand, or even smaller than that, like a grain of sand in your hand, that is so insignificantly small compared to your weight. It doesn't really, relatively speaking, it weighs nothing. And that's why we put a relative atomic mass of virtually nothing. Now, it does have a charge of -1, so we put -1 down here. Now, an electron is also referred to as a beta particle. So keep that in mind when we talk about beta decay and beta capture. It's going to involve an electron that's either captured in the nuclear equation, or decay means it's released in the nuclear reaction. So keep a lookout for a beta particle. Beta just means electron. A positron is exactly the opposite of an electron, right? So it's got the same symbol, right? It has relatively no mass, but it's got a positive charge as opposed to a negative charge. A neutron has a relative mass of 1 unit, very similar to a proton, but it has no charge to it. A neutron is neutral. So if it has no charge, it has no atomic number. Okay, now we get into another isotope of hydrogen. Okay, so the first isotope, this is the first isotope of hydrogen. And an isotope is basically heavier or lighter versions of the same element. Think of it like this. You have boxers that, they fight each other, but you have different weight classes of boxers: lightweight, middleweight, heavyweight, welterweight, light. And there's so many different categories of boxers that are categorized by their weight. Well, isotopes are very similar to that. They're heavier versions of the same atom. Okay, now here we had 1 proton and no neutrons. For deuterium, we have 1 proton and 1 neutron. See here, all we had was just 1 proton and 0 neutrons. That's why 1 plus 0 is 1. But here we have a total mass of 1 plus 1, or 2. Okay, now since it's hydrogen, it's going to have the same atomic, the 1 proton is just atomic number of 1. This is the second isotope of hydrogen. Now, when isotopes become really heavy, then they become unstable. And unstable isotopes will always radioactively decay into lighter elements, and then as a result, they'll give off radiation, hence the concept radioactivity. The third isotope is of hydrogen is called tritium, and this would be 1 proton plus 2 neutrons. So you can see you got a mass number of 3 now. Got a mass number of 3, still an atomic number of 1 because you have 1 proton. Okay, now an alpha particle is a helium nucleus. So what do we have in a helium nucleus? We have 2 protons plus 2 neutrons and 0 electrons. Okay, 0 electrons. So it's going to have a overall positive charge. Okay, so the helium, we take the helium element He. Okay, sometimes it's referred to with an alpha symbol, but usually He is how it's referred to. 2 plus 2, so we've got a mass number of 4 and an atomic number of 2. Sometimes you'll see a little 2 plus written up here. That's for the fact that it has 0 electrons. And if you have 2 protons and no electrons, you have an overall charge of positive 2. I don't think we need to have that in there. Just know that a alpha particle is positively charged. That will make a difference when we talk about certain experiments that involve alpha particles. Okay, photon, okay, like a gamma ray photon. Well, gamma ray photon essentially has no mass and no charge. It just has a lot of energy to it. So essentially, it's just going to be gamma. Now, sometimes I've seen gamma with 0, 0, but honestly, you don't really need to write that. Just gamma by itself will be fine. And a neutrino is basically a high energy particle that is released during beta decay reactions. You're going to see that happen later on. So it's just a very high energy particle. And it also has no mass and no charge. So you'll see it written as kind of looks like a symbol V, and with a little E attached to it, because it's essentially it's released along with beta particles, and beta particles are electrons. So hence the little E there. But sometimes I've seen the symbol as just a V. So a V or a V sub E would be how we can describe that. Okay. Fill in each of the blanks. So in order to fill in the blanks here, we're going to use conservation of charge and conservation of mass in order to make sure things balance. So if we look over here, we can see that the mass numbers 17 plus 1 should add up to 18 total mass units on the right-hand side. On the left-hand side, we can see we have 4. So if we're supposed to have 18 on the right, we must have 18 on the left. That means the nitrogen here has a mass number of 14. 14 plus 4 is 18. 17 plus 1 is 18. Similarly, get the mass numbers to get the atomic numbers to balance as well. So we've got 2 plus 7 would be 9. We have 1 over here. That leaves an 8 for that isotope of oxygen. Okay, in this next example here, we have, let me see, we can start, I guess, with the atomic numbers. So we have 3 plus 2. Well, one thing you should know right off the bat is we have a nitrogen. I mean, not nitrogen, excuse me, a neutron. Neutron has a mass number of 1, but no charge. Okay, so now look at what we're given. We are given 1 plus 10. That would be 11 mass units, and only 4 mass units for the alpha particle right here, He42. But if this is going to be 11 and this is 4, you know you have 7 remaining mass units, 7 plus 4 is 11. 10 plus 1 is 11. Okay, now if my atomic numbers add up to 5 and this is 0, then this has to be a 5 as well. Okay, looking at this one here, we have 1 neutron over here, so 1, 0. We got 3 neutrons over here, 3, 1, 0, but that would be 3 times 1, right? Think about that. 3 times 1, you need 3 mass units over there, okay? Keep that in mind. All right, so what do we know? We know that we have a total atomic number, total number of protons is 92. Well, I've got 36 here, 0 here, which means 92 minus 36 would be a remaining 56. 56 plus 36 is 92. Okay, and then if I add these masses together, I get 236. Well, what do I do with that? Well, take 236 and subtract 141 and 3, because it's 3 times 1. So take 236 and subtract 144, and you will get 92 mass units. And in the final example down here, if you look, we have 15 mass units here, 0 mass units from the beta particle. Remember, an electron is called a beta particle, which means you have to have 15 mass units here, 15, 15. But notice something here. We start with 7 protons, and you're subtracting 1 here. So this must be an 8. 8 minus 1 adds up to 7. Now we're going to explain how this works. How possibly can we add a proton to this, right? We're going to see how beta decay, this is actually a beta decay reaction right here. We're going to see how this works to actually increase the atomic number. Section 28.5, nuclear sources of energy. Explain fusion. Where does fusion take place? Well, if a material is so hot, it ionizes completely. That is, it becomes a plasma. And the pressure is high enough, a small percentage of nuclei will come close enough so that the nuclear force pulls them together and a huge amount of energy is released. This process is called fusion. It happens naturally in stars, which begin their lives with mostly hydrogen and a little helium. Now, it's not just hydrogen and hydrogen that can fuse to make helium, it's other larger elements too. Okay, but there's a lot of hydrogen fusion to make helium going on in stars. Explain fission. Where does fission take place? Well, fission involves the collision of a moving neutron with a heavy, unstable isotope, which basically disturbs the equilibrium of that nucleus and causes it to fall apart into smaller nuclei called daughter nuclei. So we're going to have a larger parent nucleus that's bombarded with neutrons, and it's going to split into what are called daughter nuclei. The splitting of heavy nucleus usually releases several other neutrons, which then split other nuclei. This causes a chain reaction. One example of a common fission reaction is as follows. We start with uranium-235, and we bombard that with a neutron, and that is going to split up into a barium-141, krypton-92, and 3 neutrons. Now, those 3 neutrons are going to, in turn, bombard these nuclei into other smaller daughter nuclei as well. And as you can see, you're also releasing energy in the process. What determines whether a nucleus wants to fusion, or fizzle like fission? So elements that typically have less than 60 nucleons, that means protons plus neutrons together, are more likely to fuse. So smaller elements are more likely to fuse. Heavier elements with greater than 60 nucleons are more likely to fizzle. That's why we do nuclear fission with something like uranium. We don't do nuclear fusion with that. We do fusion with smaller elements like hydrogen. Section 28.6, mechanisms of radioactive decay. Explain the process of alpha decay. Okay. During alpha decay process, a parent nucleus, for example, radium-226, decays into a daughter nucleus plus an alpha particle. If you look at this example here, we have a radium nucleus, radium-226. It has a mass number of 226, and you're going to release an alpha particle. So there's 4, and 4 minus 226 is 222, which is a radon element. And you can see that that's conservation of mass at work here. 226 to start with, 226 to end with. Now, if you look at conservation of charge, we have 88 protons to start with. 86 plus 2 is 88 protons to end with. This is known as an alpha decay reaction because you are, in the process of this reaction, you are releasing an alpha particle. Explain the process of beta decay. Okay, neutrons in the nucleus are actually the fusion of protons and neutrons. Okay, so I'm going to explain this with an actual picture in just a minute. During a beta decay reaction, a neutron in the nucleus decays into a proton and an electron, which is a beta particle. And the proton gets added to the total number of protons, like in the example to the right, where 1 proton gets added to 6 protons of carbon to become 7 protons of nitrogen. The beta particle, which is the electron, along with the neutrino, are released. So let's actually draw a picture of this right here, of this chemical reaction, nuclear reaction, excuse me, and let's see exactly how this can work. Now, to start with, I'm going to start with carbon. So I'm going to start with carbon. I'm going to draw that. How do I draw carbon-14? Well, carbon-14 is going to have essentially 6 protons, and to get a mass number of 14, you have to have 6 protons plus 8 neutrons. 6 plus 8 is 14. So I'm going to draw that. So in my nucleus, I'm going to draw, so I've got proton. Let's see here. Okay. So we've got proton, 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 proton. So I have 6 protons. Now I've got a total of 8 neutrons. So neutron, 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 neutron. And that's the nucleus of a carbon-14. I don't care about the electrons for this example. Okay, here's what I would know. If I have 6 protons, then I'm going to have a total of 6 electrons that are on the outside. Now, they're going to be at different energy levels. So I'll have 2 electrons on the nearest energy level surrounding the nucleus, and I'll have 4 other electrons surrounding that. Okay, so that's what a carbon-14 would look like. Well, how do I get carbon-14 to turn into nitrogen-14? Well, here's what happens. One of these neutrons, I'm going to pick one. I'll pick this little guy right here. That neutron is actually the fusion of a proton plus an electron. Because think about it. You got a neutron is essentially very much the same mass as a proton. They're almost identical masses. And this has virtually relatively, 0 relative mass. And if you look at the two charges are essentially going to balance out each other. So a neutron is really the combination of, smaller particles. And so what happens in this process is a neutron is going to split up. Okay, and when a neutron splits up, one of these electrons gets released. That's the beta particle. And this proton is going to get added to the 6 that are here, making 7. So now you'll have 1, 2, 3, 4, 5, 6, 7 protons, and a total of 7 neutrons, because you just got 1 neutron. You got rid of 1 neutron, right? So you got 7 left. So 1, 2, 3, 4, 5, 6, 7. There's your new nucleus, right? That's what you got going on, plus the beta particle that gets, whizzed away, and a neutrino. That's, the high energy particles are exiting. But look at what's left here. 7 plus 7 gives you a mass number of 14. 7 protons gives you a brand new element of nitrogen, and a release of an electron, which is a beta particle. Here's the easiest way to know about alpha particle, alpha decay, and beta decay. Really easy to tell. In alpha decay, the mass number, which is A, always subtracts 4. You start with this, subtract 4. The atomic number always subtracts 2. Start with this, you end up with 2 less. Okay, so in alpha decay, your other daughter nucleus is always going to be 4 less mass and 2 less protons. For a beta decay reaction, here's what you're going to end up with. You have your nucleus, I'm going to call it X. This X represents your daughter nucleus. And it's going to be, if I start off with some parent nucleus as X, A, and Z, well, you've got your beta particle and your neutrino. If Y is your daughter nucleus, you're going to end up with the same mass, right? Because that has no relative mass, but you're going to end up with 1 more atomic number, 1 more proton than you had before. Okay, so we add a proton for beta decay, but the mass stays the same. For alpha decay, okay, we have a parent nucleus of mass A and atomic number Z, decays into an alpha particle that has a relative mass of 4 and 2 protons, would have a daughter nucleus of A minus 4, right? 4 less than that, and an atomic number of 2 less than that. Explain the process of gamma decay. Well, that one's easy. A gamma decay reaction just simply involves the release of gamma radiation. So, for instance, when the mass number and the atomic number are just going to be the same, it's going to be a release of high energy. So in certain nuclear processes, you'll get from one isotope to another, and as you do so, you can see that sometimes it's just going to result in the release of a gamma particle. Okay. So in this example, we have uranium-238, and it's going to decay into lead using the following decay chain. The first one, and we're going to do these in different parts here. We're going to have an alpha followed by a beta, beta, alpha, 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 beta, beta, alpha, alpha, beta, alpha, beta. And we're going to essentially mark where we're starting from, and we're going to show how the decay would happen. So I'm gonna point I is going to be the initial value, and that's going to be at uranium-238, 92. So I go to the grid. Okay, let me make this a little smaller here. 238 is right here, and 92 is right here. So I go all the way up to that point right there. That's going to be our starting point. So now we are going to start. What I like to do is I like to cross off these as we go. Okay, now remember what these look like. Alpha decay, we're going to do what? We're going to, the daughter nucleus that we end up with is going to be 4 less on the mass number and 2 less on the atomic number. Okay, beta decay, the daughter nucleus is going to have the same mass, but it's going to have an atomic number of +1. So we're going to add one more proton. Okay, so let's actually try this one at a time. So I'm going to start with an alpha decay. So an alpha decay means I start with 238 and I have 4 less mass. 238 minus 4 would put us, and then down to 234, and it's going to have 1 fewer or 2 fewer protons. So that would be down 1, 2, 3, 4, and over 1, 2. That would put us right here. Okay, so there's our first reaction right there. Okay, and then and cross them off as you go. And then we have a beta reaction after that. Beta reaction just involves the adding of 1 more proton, but the mass stays the same. So the mass is still at 234. So that's going to look like this. Just going to make it 1 proton heavier. Because remember, this axis right here is the atomic number, which is the number of protons. All right, and so I cross that off. And then the next one is a beta reaction right here. So I'm going to cross that off, and I'm going to add 1 more proton. Okay, now I have an alpha, 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 alpha. I have 4 alphas in a row. To do 4 alphas in a row, I'm going to go down 4 over 2, down 4 over 2. So that one will look like down 4 from this point here, down 4, 1, 2, 3, 4 over 2. That'll be here. Down 4, 1, 2, 3, 4 over 2. That'll be here. Down 1, 2, 3, 4 over 2. That'd be here. And then finally one more, down 4 over 2. That would be here. So that would be 1, 2, 3, 4 alpha decays in a row. Okay, now we've got 2 betas in a row. So 2 betas in a row would be add 1 proton, add 1 proton. That puts us right here. Okay, now we have 2 alphas in a row. So down 1, 2, 3, 4 over 2. Down 1, 2, 3, 4 over 2. Okay, now we have a beta reaction. So we have 1 beta. Okay, and then finally we have an alpha and a beta. So that would be down 4 over 2. That puts it right here. And then finally add 1 more proton. That puts it right here. And the final nucleus that you end up with is lead with 82 protons and a mass number of 206. And that's exactly what we're trying to get, is how does this decay into a lead nucleus? And we're going to label that as F for the final. That's the final nuclei that this decay chain. It's called a decay chain because it's a chain of events that happen. Okay. Now, pause the video and try the second example yourself, starting with Pu, which stands for plutonium-239, and see how that decays into a lead nucleus. Okay, now that you've had a chance to try this one, let's go ahead and check our work and see how we did. So we're starting with plutonium-239 and 94 protons. That would put it, for starters, right here, 239 and 94. Okay, puts it right there. Okay, now for starters, we're going to go 1, 2, 2 alpha decays in a row. So I'm going to go down 4 over 2, down 4 over 2. And there's my starting 2 processes. Okay, then I'm going to go beta, which means add 1 proton, keep the mass the same. Then I'm going to go 2 alphas in a row. So down 1, 2, 3, 4 over 2. Down 1, 2, 3, 4 over 2. Okay. And then we're going to go 1 beta, means add 1 more proton. Then we're going to go alpha alpha. So down 4/2, down 4/2. Then we're going to go 1 beta. I'll first go ahead and connect those. Okay, we're going to go 1 beta. That means add 1 more proton. And then we're going to finally end this up with an alpha alpha beta. So down 4/2, down 4/2. Those are your 2 alphas, followed by 1 beta, which puts you right at lead 82 with 82 protons and 207. So this is lead 207. That's going to be our final daughter nuclei right there. Okay, let's take a look at the following example. An atom of isotope polonium-214 is initially at rest when it decays into a lead nucleus and an alpha particle according to the equation polonium-214, and that decays into lead and then the alpha particle. So we know the alpha particle is 4,2. Remember, alpha particle is helium 4,2. It's a helium nucleus. You could write it as He or with an alpha symbol. Either one's fine. Here they wrote it as an alpha symbol. So use your conservation of mass. We have 214 here, 4 here. That must mean you have remaining 210. So it decays into lead 210. You know that you have 84 protons, 2 protons here, which means lead has to have 82 protons. So there's your basic nuclear equation, all right? And that's what part A is, just filling in the blanks here. Now we're going to use this table of information about these particles to answer the questions below. Do keep in mind that 1 atomic mass unit is equal to 1.660539 times 10 to the negative 27 kilograms. That will be handy when we try to convert. So if we actually multiply this right here and put it in atomic mass units, that means that if I take this and I divide it by this many kilograms, I'm going to get 4.00250.762 atomic mass units. Now, how I got that again, I take this mass right here, which I guess I can show it right here, 6.64, 632 times 10 to the negative 27 kilograms, and I multiply that by 1 atomic mass unit is equal to that, right? 1.660539 times 10 to the 27. So I basically take this, divide by that value right there, and that's how I got the that's how I got this value right here. Similarly, take this and divide it by that equivalence to 1 atomic mass unit, and the mass of the lead nucleus is about 209.9788081 atomic mass units. Okay, so now for part B, calculate the velocity, magnitude, and direction of the lead nucleus. So if you think about it, you're starting off with a nucleus right here, and one particle is going one way, the other particle must go in the other way. This is conservation of momentum as its finest. If you have one object that starts here at rest, right, and then sometime later it breaks off into 2 parts, one of which goes this way, the other object has to go the other way. Okay, that's conservation of momentum. And our conservation of momentum equation is M1V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. Now, both this right here kind of includes the whole polonium nucleus to start with. And it's essentially the whole thing is starting at rest. All right. And that's kind of how I'm going to start this thing is the mass, the big mass of the polonium nucleus times V. The whole thing is at 0, which means the sum of the two momenta have to add up to 0, which means it's equal and opposite final momenta. All right. And that's exactly what we have. M1V1 final is equal and opposite to M2V2 final. And so we know the mass of the alpha particles going this way to the right. Well, that means that the lead nucleus A has to be going left because it's going the opposite direction. And we're going to solve for that. So if I want to let this, let's say I let this be, I don't know, V2. Okay, then I'm going to solve for V1. Okay, so V1 final is going to be negative M2 V2 final over M1. And so we have negative mass 2. Now I'm going to use everything in kilograms for now. So negative mass 2 would be referring to the lead, the alpha particle. So everything about the alpha particle, if that's V2, that's going to be mass 2. So 6.64632 times 10 to the negative 27 kilograms times its velocity, 1.9267 times 10 to the 7 meters per second. Divide that by mass 1, which is the lead nucleus, 3.48678 times 10 to the negative 25. Negative just means it's going the opposite way of right, which would be left. So the velocity is going to be, when we put that in our calculator, about 3.6, we get about negative 3.67 times 10 to the 5 meters per second. Or you could just say 3.67 times 10 to the 5 meters per second left. Right? This is, again, conservation of momentum from AP1, right? That helps us deal with part B. Okay. Now, how do we figure out the total energy released during this reaction? Well, this is going to be conservation of energy. See, what we know is the total energy released, which I'm going to call Q, is equal to the kinetic energy of the alpha particle plus the kinetic energy of the lead. Okay, so what we have, let's figure out the kinetic energy of the alpha particle. That's going to be 1/2 mv squared. So 1/2 times 6.64632 times 10 to the negative 27 kilograms times its speed, 1.9267 times 10 to the 7, oops, that's a 7 squared. Okay, now make sure you practice putting this in your calculator yourself, because these are really high, super small numbers rather, and a lot of scientific notation involved here. We get about 1.234 times 10 to the, negative 12 joules for the kinetic energy of the alpha particle. The kinetic energy of the lead, right, is also 1/2 mv squared, but it's 1/2 mv squared of the lead. So the mass is 3.48678 times 10 to the negative 25 kilograms times its speed, which we just found in this part right here, to be about 3.67 times 10 to the 5. Again, don't forget to square it. When we put that into a calculator, we get 2.0 3 times 10 to the negative 14 joules. Now, when we add that together, Q is going to be 1.26 times 10 to the negative 12 joules. Now, that's one way to answer this, okay? But do keep in mind that there is a conversion, and the conversion goes 1 mega electron volt. We talked about electron volts in our atomic and quantum physics unit earlier, is equal to about 1.602 times 10 to the negative 13 joules. That's the conversion between mega electron volts and joules. So if I multiply that or divide by 1.602 times 10 to the negative 13 joules in 1 mega electron volt, I'm getting about 7.85 mega electron volts, right? That's a lot of energy. Okay. Calculate the mass of the original polonium nucleus. Okay. Well, one of the things that we know is that this is where mass energy equivalents come into play. The total energy released, this is the total energy released, is equal to delta M C squared, where delta M is the mass defect. Okay, remember the mass defect is the difference between the mass of all the little parts of the that make up the atom and the mass of the atom itself. Okay, and that may seem kind of counterintuitive, like, well, how could the masses be different? Well, the fact is you're going to lose a tiny fraction of mass in any nuclear reaction because some of it has converted to energy, hence the concept mass energy equivalence. Okay, so we also have another conversion that says 1 atomic mass unit times C squared is equal to 931.5 mega electron volts. That will become very handy as we go. Okay, so I know that I could rewrite this as delta M times 931.5 mega electron volts, right? Because 1 C squared, I'm substituting for C squared times 1 atomic mass unit. And therefore, if I solve for delta M right here, I get delta M is equal to Q over 931.5 mega electron volts, which was 7.85 mega electron volts. We just got that from the previous example. All right, and that's divided by 931.5 mega electron volts and per U, and that would give us 0.008427 atomic mass units. Okay, that would be the original mass of the polonium nucleus. Now, or actually, no, that's the mass defect. That's the difference in mass. That's not the original mass. I'm sorry. So what we know is that the mass defect, the difference in the mass, is going to be the mass of the polonium minus the mass of the lead minus the mass of the alpha particle, right? That's the difference in all three of these. Okay, so that's what we're going to kind of figure out. So the mass of the polonium one, if you kind of add the other ones, is going to be add the mass of the lead, add the mass of the alpha particle, and you get the mass of the polonium. So that's how we figure this out. So the mass of the polonium nucleus is going to be the mass defect, which we just added that, and we have 0.008427 atomic mass units. The mass of the lead that we add over there, we've got that right there. That's that number here, 209.97880881 atomic mass units. 209.97880881 0.081 atomic mass units, plus the mass of an alpha particle, which is 4.00250.762 atomic mass units. 0.762 atomic mass units. Add those together and we get 213.98974.272 atomic mass units. Now, if we use the conversion that we saw, where did we write this? We wrote this a little while back. Trying to find, there it is. That one atomic mass unit is 1.660539 kilograms. That you can convert it. So you can have an answer in atomic mass units like we have right here. That would be fine. Okay, and you can have an answer in kilograms. So if you divide that by multiply that times 1.660539, you'll get 3.55 times 10 to the negative 25 kilograms would be the mass of the original polonium nucleus. Okay, so in part E, calculate the binding energy in joules of this polonium nucleus. In other words, the mass of the proton or the neutron is going to be this value right here. So the binding energy, okay, we're going to call that BE. Well, the binding energy is equal to delta M C squared. Well, we know what delta M is, the mass defect from the previous problem, 0.008427 atomic mass units, times the conversion of, we can write 931.5 mega electron volts per 1 atomic mass unit C squared times C squared. And you can see a lot of stuff cancels. Cancels, and you have your answer in mega electron volts. In which case you're simply multiplying by those, and you get the answer that we got before in the previous problem, which was 7.85 mega electron volts. So the binding energy, okay, it's the energy that bound the polonium nucleus together in the first place, was the same as, go back, the total energy released. Why does that make sense? Why does that make sense? Right? The energy that you're binding everything together with has to be the same that you release it with when you break up what is bound together. Section 28.7, half-life, decay rate, and exponential decay. Suppose you have a sample radioactive nucleus material, a block of uranium atoms, for example. These atoms have unstable nuclei, so they decay to stable elements such as lead. When does the entire sample of pure uranium turn completely into an entire sample of pure lead? Well, here's the thing. It's going to take 4.5 billion years for half of the sample of uranium to decay into lead, but that's only half of the sample. About how this is going to work, to decay into pure uranium into pure lead, well, that's virtually never going to happen because you're always going to be infinitely splitting your sample in half and then another half and then another half and another half and then another half. So you're always going to have some uranium. It's just going to be infinitely smaller and less measurable over time. But it takes 4.5 billion years just to cut it in half. So think about that much. So it would take, right, a really, if you think about it, it would take an infinitely long time in order to decay completely from one into the other. What does half-life measure? Well, half-life measures the time it takes for half of the material to decay. So you can't really measure the whole life because, like I said before, the material is infinitely cutting in half. every single time. Therefore, we're never fully going to eliminate the original material. Okay, we're always going to keep cutting the original material into smaller halves and so on and so forth. So let's take a look at this graph right here. Okay, and we'll kind of close out our lesson with the following example. Suppose you start with a mixture of 200 grams of manganese 52, which decays half of its stuff every 5 days, and 100 grams of thulium 167, which decays half of its stuff every 10 days. On the graph below, draw the amounts of each isotope remaining in your mixture as a function of the days elapsed. Graph both. So I'm going to do these in two different colors just so you can see. I'm going to be graphing in black the manganese 52. Okay, and I'm going to be graphing in blue the thulium 167. Okay, so now in black, I'm starting with 200 grams of this particular isotope. So 200 grams at time equals 0. I'm going to place a dot right there. Okay, now every 5 days, you're going to cut it in half. So at 5 days would be right here. Now it's down to 100 grams. So make a dot right there. Okay, at 10 days, which is another 5 days, it's going to be down to 50 grams. Okay, and you can see how it's, decaying closer and closer to 0. Okay, at 15, it's going to be down to 25. Okay, and just keep cutting in half. 20, now you're down to 12 and a half. 25, you're down here. At 30, you're down here. 35, you're down here. 40, down there. Very, very close to 0. So that is your original graph of manganese 52, or at least the decay of manganese 52. Okay, so by contrast, the thulium 167, we only start off with 100 grams of it, and it has a longer half-life, twice the half-life. So we start off with 100 grams. Okay, after 10 days, it's going to decay into 50 grams of that. So we lose half the stuff. So it's at the same dot here. At 20 days, another 10 days pass, and now you're up to 25. 30 days, now you're to 12 and a half. Okay, and then finally 40 days, you're down to about a little between 6 and 7. So this would represent the decay rate of thulium 167. Okay, I hope you found this lesson to be helpful, and please remember to pause or rewind necessary and list any and all question marks that you have so that we can explore them together in class. Thank you.